Hello guys. Now we go for ways or the way using Lagrange multipliers to build up dual forms from their primal while solving linear problems, linear optimization problems. Consider now, of course, we are just going to consider Lagrange multipliers to build up those forms, those dual forms. So this will complement the previous videos in which we have discussed ways of building up dual forms, basically like considering some tricks, so to speak. Okay. Now we're going to reformulate this primal in its dual space using Lagrange multipliers. Take a look at the problem. First of all, it is a linear, consider it's a linear problem, so of course the objective function and constraints are linear, but this requires, as you can see, Tucker multipliers instead of Lagrange multipliers, but the way of formulating is basically the same. First of all, I need to build up the Lagrangian function. So here we have our Lagrangian L of x lambda. Lambda is here referring to the Tucker multipliers. Okay. So here I have my objective function of x minus, again, I just told you this, guys. We typically use minus for maximization forms and plus for minimization forms, but that also depends on this sign over here. For now, just consider minus related to the maximization. However, that's going to be a bit confusing, the next example, but it's not important for now. We're going to go into that later. So we have lambda here times our constraint equal to 0, of course. So this b has to be on this side, on the left side. And of course, we make this this constraint equal to 0, as shown here. And then the solution for this, the dual for this, will come after differentiating our Lagrangian in terms of x, this variable x, okay? Ensuring lambda is greater than or equal to 0. This is related to the Tucker condition, I suppose you guys remember. And this x in the domain, or x in the feasible set, D is related to the feasible set for us, feasible region. Okay. This basically means we have a solution for x. This basically means that at least a single point or a single solution happens for our maximization problem. Otherwise, we are not going to have the solution, of course. So from this, we can just reformulate our problem, of course. So our problem is in here, okay? Just showing this in terms of a transpose of a vector times x, of course. And oh yeah, that's what I told you guys. So we can go. So differentiating in terms of x, of course, we're going to have this, all this differentiate in terms of x. This will be c transposed, or vector c. Okay? Those are the coefficients multiplied by each element we have in vector x. This could be a bold x, just to be sure it's a vector. It would be better if it were like a bold vector. So differentiating again in terms of x here, we're going to have A transposed lambda. So minus A transpose lambda, and this is going to be 0. And this derivative is equal to 0, of course. So on top of this, we're going to have that A transposed, the matrix A transposed, product by lambda, by vector lambda, is going to be equal to C, as you might observe over here. You know, there's something already interesting over here. Probably you guys remember from the previous video that I told you that the matrix A would contain the coefficients of constraints. C would become our bounds. Take a look. But before, in the primal problem, C was related to the coefficients of our problem being multiplied by X. But we are going to discuss that if you instance, no problem. So this is our Lagrangian again. I can just open up by distributing lambda over here on this side. So we are going to have minus A transpose lambda X plus lambda B plus lambda B as in here. Of course, given we found this result from the previous differentiation, we can substitute as we did before, as we did in like a couple of videos before. We can substitute this term, A transpose lambda, by C. If we substitute, we are going to have C transpose X minus C transpose X plus lambda B. Observe this, we are going to cancel out those terms, and we will have lambda B. Take a look at this. This is quite interesting. Lambda B will become my objective function for my dual problem, for my dual form. What is lambda? What was at least lambda? The Karushkin-Tucker multipliers, a vector with the Karushkin-Tucker multipliers. If you prefer, you can just assume for Lagrange multipliers if you are solving for the equality. Going, so we cancel out those two terms, and now, because we had a maximization problem, now we have a minimization problem in terms of lambda B. And of course, everything that is vanished during our substitution is kept over here. So we keep A transposed lambda equals C. And there is something quite interesting that we need to ensure. Remember, Karushkin-Tucker multipliers, every multiplier has to be greater than or equal to 0. This is our minimization form. Quite interesting, isn't it? Now you know what? Now we are going to do the opposite. I just invite you guys to try. So just think, pause the video over here, try to find the dual form given this is the primal problem. Okay? You already have it. You know what is the other form. If you're given this as the primal, you know dual would be that maximization we've seen before. Try it and then get back. So starting the solution, first of all, we need to build up the Lagrangian. That will be minus lambda B in here. You might see that here, besides minimizing, I'm using minus here. We can discuss that later in a different class, because I told you guys that, okay, if it's a minimization, should be plus here, but that also depends on the, as I told you guys, on the form I have for my problem. In the previous maximization form, I had like a small less, it was like smaller than or equal to. Yeah, that will interfere, and this equal also will interfere. For now, it's okay. Just consider, okay, someone told me it's going to be minus. Again, this is the Karushkin-Tucker multiplier X, or in this case, it's much more like a Lagrange multiplier, as I might see, because it's for an equality constraint. So you can say, okay, this is a Lagrange multiplier times my constraint. What it is my constraint? A transpose lambda minus C to make it equal to 0. Okay, so I can open up this. Of course, I have to differentiate in terms of my variable lambda. So if I differentiate in terms of lambda, I will have b over here on this side, minus, differentiating in terms of lambda, I will have A transpose x, minus A transpose x equals 0, of course. This will become A transpose x equals b, as you know, and this A transpose x equals b can be substituted in my Lagrangian. So here I just decided to open the Lagrangian by distributing x. Take a look. I have lambda b minus A transpose x lambda plus C transposed x plus, because of those minuses over here, of course. So this will be, after differentiating in terms of lambda, we had this result. Of course, A transposed x is going to be equal b, because I bring this as minus b over here, multiply both sides by minus 1, so A transpose x equals b. By substituting A transpose x over here by b, I will have lambda b minus lambda b plus C transpose x, that is C transpose x. As you might see now, I have the objective function for the other problem, for the maximization problem again. Take a look over here, please. So from this, I know I have to maximize C transpose x. But what about the constraints? I need to bring the constraints. I think you guys remember about the constraints. We are going to use this table once more to define the operators for the constraints. First of all, the constraint that was vanished actually after the substitution was a constraint based on this as the primal problem. Okay, and of course the variable lambda over here is going to interfere directly in the first constraint, or in the constraint we will have for the maximization problem that we are finding at this point. Okay, so if this is greater than or equal and we are in minimization, I think you guys remember in minimization, greater than or equal for the variable. Okay, the variable must assume non-negative values. So of course I need that will impact the operator for my constraint, as we've seen before, like in 3 videos before, I'm not sure. So at this point, this was the term that was vanished from my Lagrangian. And I suppose you guys remember it was equals to 0. And of course, this is the same as, now there is a small difference, okay? This will be b minus A transpose x greater than or equal to 0. So I need to define the operator before bringing this b on this side, or even better, before multiplying both sides by minus 1, because that will affect this operator. So I knew that my variable lambda was greater than or equal to 0, so my constraint associated to that particular variable in my dual form will have this operator greater than or equal to. From this, I can bring b to the other side, multiply by both sides by minus 1, so this will be inverted. This inversion is really related to that minus sign that we used in our Lagrangian for this minimization problem. But I'm not going to discuss that in detail. Not in this course, probably, because that's really related to optimization in some details, so to speak. But actually, at some point, we are going to discuss about the Cauchy-Tucker conditions, and this will become like really, really obvious. So now we can see both forms, the primal and its dual, side by side, and we're going to notice some few things. First of all, the Lagrange multiplier of the first becomes the main variable for the second. Just getting back, the Lagrange multiplier, here I decided to apply a Lagrange multiplier multiplying this constraint by lambda, and that lambda became, take a look here, the coefficients I have for my dual form. Okay? Again, this b here becomes, which are the bounds for my constraints, become coefficients in my dual form. And vice versa. This bound here, coefficients here. I multiply this constraint by a Karush-Tucker multiplier x, and that x became the variable for the other problem. Take a look here. If I have here, of course, this variable lambda will affect the operator of this constraint. And the variable x has no bounds here, so that will make my operator of the constraint for the minimization form equals, being the operator equals 2. There are some interesting stuff here. Again, a, if we have the coefficients for our constraints here as a, here it will be the transpose of this matrix A. Quite interesting, isn't it? Now I think I just invite you to think, pause the video here, think about this. Lagrange multiplier or Karush-Tucker multiplier of this form, which is associated to this constraint, will become the variable I have for my optimization problem over here. My matrix will be transposed. My bounds will be my coefficients. And the range from a variable x here, which has no range, will interfere according to that table in the operator for my constraint or constraints. It depends, of course, if I have many or not. Okay? The same happens on the opposite. C will interfere over here, right? C, my bound, will become my coefficient, or my vector of coefficients. My x multiplying this constraint, which is a Lagrange or Karush-Tucker multiplier, in this case, as it is equals 2, could be a Lagrange multiplier. That will become, of course, my x over here. As my lambda is greater than 0, you guys remember that I did the substitution of this guy over here, which should be greater than or equal, but before multiplying both sides by -1, this was b minus ax equals 0, and then we had greater than or equal, and bringing b to the other side and multiplying by -1, we've got this result. Just think about this. This is quite interesting. Look at the Lagrangians. So if we look at the Lagrangians, we see again the Lagrange multipliers or Karush-Tucker multipliers from this form become the variable for the other. Take a look here. The Lagrange multipliers of this form become the variable for the other. Okay? The coefficients for constraints are transposed, simply transposed. The coefficients, they are multiplied by x in this form. In this form, they are multiplied by lambda. I think you guys remember from previous videos that we were talking about that exactly. Take a look. Bounds here associated to coefficients here, and bounds here as coefficients here. It's so way interesting. I invite you guys to think once more about this, and then you go for the next video. Okay? See you.